Jai Hind everyone. I, Suvarna Mujumdar, we are going to have discuss about Karnaugh map. Before going to discuss about Karnaugh map, we first go through what is Boolean function and how we can use this Boolean function to represent any digital circuit. So Boolean function are nothing but a mathematical expression where we can use binary variables as an operator and we can assign a value either one as a true or false. This Boolean expression can be expressed in the form of truth table, logic diagram, and or you can say it is a mathematical expression where we can have. So Boolean function can be of three ways we can express them, either as a truth table expression, as a mathematical equation, or as a logic diagram. The digital circuit, that whatever we design or we analyze, we have to represent that digital circuit in these three forms. And when we are going to design a circuit or when we have to analyze a circuit, we have to make it simplified and optimized by using a Boolean function so that we can have a cost-effective digital circuit. So the basic Boolean algebra which we are going to use with an operators like ANDing operator, ORing operator or NOT operator, and we have different Boolean variables like we can use ABC or XYZ as a Boolean variables to represent a number digits in the forms. For example, if we have a 3 input system, then in that case we have 3 variables and we have the combination of these 3 variables. So with each variable have 2 values, either 0 or 1. So we can have 3, if we have 3 variables and suppose A, B, C, then we have 2 raised to power 3, 8 combinations, as A may be true, A may be false. So when we have to represent a system, we can use a Boolean variables and operators to write an expression, that is Boolean expression, and we can have a combination, 8 combination from 000 to 111 with 001, 010, something like this. And then we have this as a truth table where we can apply all the input combination and we find the output for each combination. Now when we go through this truth table, we have 2 options to represent a system, either as a sum of product expression or we can go with a product of sum expression. So we will see what is the difference between these two and how we are going to use these 2 expressions to design our logic diagram. Now, in this lecture, I am going to cover mainly about the Karnaugh map, how we can understand this Karnaugh map, how it is useful in minimizing the Boolean function. So, Karnaugh map is oftenly known as K-map. We call it as K-map. It is a visual method for minimizing Boolean expression. The another method for minimizing is Boolean algebra theorem, or we use different De Morgan's theorem and different postulate to minimize the expression so that we have a cost effective digital circuit. But in that case we have to remember all the properties and all the theorems related for the manipulation, and it needs some time, or we can say it is a tedious task if number of variable is more. So when number of variable is 2 or 1 or 3 maybe, then in that case we will go with Boolean algebra theorems. But if number of variable is more than 3, like 4 or 5, in that case we have to use K-map, and it is a very easy way to reduce the or we can say minimize the Boolean function. So K-map is a type of truth table, or we can find it how it is related to a truth table, and it is a diagram made up of squares, or we can call it as cells. Each of these squares represent the min terms or max terms. So if there are n number of variables, then we have in K-map we have n 2 raised to power n maps sorry, squares. So suppose we have 2 variables, then we have 4 cells or 4 squares in a K-map. So in case of minimization using K-map, First of all, we have to know how we can group ones and zeros. Actually, we have two outcomes. Either as a true outcome, we can call it as ones, that function is true for 1. And if we say that the outcome is in the form of zeros, then we can say that the system is valid for 0 output. Then we will map the outcomes, or we can group them for zeros. Then we can have a formation of min terms. When we group 1, we call it as min terms, and when we group for zeros, we call it as max term. Then we have to identify the adjacent cell so that we can minimize the K-map. We have a group formation rules, and after group formation rules, we have this simplification SOP and POS form. So now in this lecture, we are going to discuss about SOP and POS form with an example of K-map simplification. We can have a 2 variable, 3 variable K-map or 4 variable K-map. But in this particular lecture, I am going to cover about the 4 variable K-map, as it is a more useful, because in case of 2 variable and 3 variable, we can go with Boolean algebra theorems or postulate. So first of all, we will discuss what is min term and max term. So as I told you that we have to first go through the truth table. So here, for example, this truth table is having 3 variables x, y, z. And in this x, y, z, the function is valid, or we can say the function is having 2 outcomes, either 1 or 0. So for the input combination 0, 0, 0, the output of function is 0. So this 0 is considered as a max term. Then in 0, 1, 0, if input is 0, 1, 0, again we have 0 as an output. So it is considered as a max term. We represent it as a max term. Then the for case of 0, 1, 0, 0, 1, the output is 1. So we have a group of 1, so it's called it as min term. So group of zeros are called as a max term. So first of all, we have to find whether we are going for SOP form. Then we will go with the grouping of ones. If we are going to minimize the K-map for POS form, that is product of sum form, then we are going to group for zeros. So the procedure for placing min terms in a K-map. So first of all, the statement is given to you. Then from the statement, we will go through this truth table. So we create this truth table for different input combination. From this truth table, we have to place this zeros and ones in the K-map. So for example, if we have to place ones in case of K-map, so this is a 3 variable K-map. So here in this 3 variable K-map, we have 3 variables A, B and C. So here A is having 2 values, 0 and 1. And B is having, again, B and C is having 4 combinations, 0, 0, 1, 0, 1, 1, 1, 1, 0. When we are drawing this K-map, and in this case, we have to make the cells. As I told, there are 3 variables, so we have 8 cells. We have to keep this in mind that we have to use gray coding. Single bit change, single bit transition is the must for numbering the this K-map cells. So each square box is known as one min term, or it may be a one max term. It represents one min term, or it may represent one max term. But this cell is having a number. In terms of our, we can say BCD number system, or we can go with binary numbers. So for numbering this cell, we number it as 0. So to represent it in binary, it will be 0, 0, 0. That is A dash, B dash and C dash. So this is 0. Then we have 1. Now this will not be 2. This will be 3. We go with single bit change, single bit transition. So it is 0, 1, then 1, 1 and then 1, 0. Similarly, here it will be 4, 5. So from the expression or from the truth table, we will find for which min terms or for which input combination we have the output will be 1. And we will place that 1 in that particular cell. For this example, in this case, For in this example, the function is valid or function is 1 for the input combination A dash B C dash. So here it is 1 and the next input combination is ABC. So for ABC 7 it is 1. So in this way we place here 2 ones. Now if we have some function like this Boolean function, so from this Boolean function we have to find the truth table. First we create the truth table, then we will go with K-map and we will minimize the expression. So this expression is given to us which is having 4 minterms as it is in the form of SOP, that is sum of product. We have 4 products, 4 minterms and we mix it and we make one expression. So it's 4, so it's sum of products. But in here you can find that actually in this case there are 4 variables and rest of that there are 3 variables, or we can say that it is a 3 literals. But as there are 4, so the function is of 4 variable, but it is in the form of SOP form. So we will go with, we will find the number of minterms for which this function is valid. So we will go with expansion form. We will expand this function by just adding the remaining one. So in this first case D is missing, so we add this as a product form D plus D dash, because by identity this value will become 1. Here A is missing, so we add A plus A dash on in the multiplication form. Then we will go, this literal is having all the values, so we don't go with this. Here we are again missing D, so we add D plus D dash. We multiply. Now if we expand this, A B dash C dash A dash B. D plus A B dash C dash D dash. Now we will convert this into binary number. So from here you can find it is 0001. It's 0000. It's 0. Sorry. It's 1. It's 1010. It's 0 0 1 0 0 1 1 0. So 1 0 0 1 9 and it's 1 0 0 0 8. So this function is expression is valid, or we can say true, for 1 0 10 2 6 9 and 8. So these are our minterms for which our function is valid. So we say it's a 0 1, then it is 2 6 8 9 and 10. 1 2 3 4 5 6 7. 3 3 6 and 7. We find these values for which our function is 1. Now we will draw a K-map for this. So we will draw a 4 variable K-map. Now in this K-map we are having AB and CD. So it's 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. We will number it. Cell number 1 2 3 4 5 7 6. So our system is, our function is valid for 0 1 2 6 8 9 and 10. So here we will go through and we will find that it is having Now if we find this, there are adjacent cells where we are having 1. Remaining cell, I place it as 0, because for other things it is the function is having the false value. So we place it 0. Now from here we have to make a group. So for grouping, we have to find the adjacent cell. So first we will look for an octet or a 16 group cell that all the cells are having 1 as a function. Then we can make it as a simplest function, it is equals to 1. But then if it is not there, we will go over an octet that a consecutive or adjacent cell is having 1 value. But in this case again we are not having any octet there, where we are having 8 cells which is having the 1 value. So now we are going to find the quad, that is 4 cells, and to find these 4 cells we have to just fold this one from left up to down, from left to right. So here in this case we find that it is adjacent, like these 2 and these 2. These are 4 are making one quad. So from this quad we will find that A is changing, so we remove A. B is not changing, so we place it as B dash. Here D is changing, so we remove D, and remaining C is there. So from this quad we are having an minimized expression, that is B dash C dash. Now we have to make a pair of ones. So we find that there is one here at 10. Then we are having one at 2 and 6. So we can find that if we fold it something like this, the last these four are making one quad. So when we club this 4, we find this A is missing, so only B remain, B dash, and if you find here B is there and D dash is there, because C is changing. So in this way we have to, like this one is remaining, so we have to make it pair with this. So it is not having any quad, we are having a pair. So in this pair we will having A dash, C and D dash. So the minimized expression for F will be B dash C dash plus B dash D dash plus A dash C D dash. So from this given expression where we are having 4 minterms, so in this case we required 4 AND gate and 1 OR gate. We minimize this expression to 3 AND gate, and as well as also we minimize the number of input for AND gate. Like in this case the input for an AND gate will be 3 or 4. But for this expression we have 2 input AND gate, 2 input AND gate and 3 input AND gate. So we minimize the overall function, or now we are going to minimize the logic diagram also when we are going to draw this using this expression. In case if we are going to have a max term, the earlier one example was of minterms with where we are having SOP form. Now if we have a product of sum expression, if we have to draw a logic diagram using NOR gate instead of NAND gate, if NOR implementation, that is first ORing then ending, or first in SOP form we are first ending then ORing. So there are single OR gate and n number of AND gates are there. But in case of product of sum we have n number of OR gates, and it depends on the number of minterms and max terms and one AND gate. So here we have to represent, for example in this case there is a 0. So for 0 if we read it as, so it is 111. But when we are going to represent it as in max term form, we have to make a complement of this and we have to write this. It's a 30, but when we have to write in the KMF form, we have to take the complement of it and then place the value 0 there. So we will solve one example for this case. So suppose we have a given that expression, it is summation sign is given. This summation sign represent for SOP form. So the function is given in SOP form, but the simplified function we need to be in POS form. that is product of sum. And when we have to write the expression in POS form, we use the sign multiply. Okay. So in this case, again, there are 4 variables. So we will draw a 4 variable K map directly as it is given. We have number of literals. So A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay. We will name it 0, 1, 2, 3, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 14 and 15. Now, as the given expression is SOP form, that it means that this function is valid for these numbers. That for 0, if input is 0, then this function is having valid output 1. For 1, again it is having 1. For 2, 5, 8, 9 and 10. So for these terms, our function is valid true output. But we have to simplify this expression for POS form. It means that we have to make a group of zeros. So we have to first place the zeros in our K map. So remaining terms, I placed it as zeros. Now we have to make a group for these zeros. So again, the rule is same. We have to find the adjacent cells and we make the group. We have to first find for a octet or a 16 group. Then we go for octet. If octet is not there, we go with quad. Quad is not there, then we go with pair. And if nothing is single cell is there, then we make it a single cell representation with 4 variables. So in this example, now we have to make a pair of or we can say a grouping of zeros. So we first go with the grouping of zeros. So we find that there is a, and when we make a quad for this or pair of these groups of these 4 zeros, we find that we will having A and B are the values which are not changing. C and D are changing for all the 4 cells. So it's having A and B. Now when we have this quad, we name it as, here C and D is not changing, but rest A and B are changing. Now remaining 2 zeros are there, and if we go, we can make it as pair also, but to minimize the circuit, we will go for quad. Now when we are going to pair this, we find this A is changing, so here B is remaining only, so we write as B, and from here you can find that C is changing, D is having 0 value, so I place it as D dash. So when we write the expression, it is in the SOP form. But the question is, we have to write it in a POS form. So when we have to convert SOP into POS, what we have to do? We have to change, we have to complement it and changing like ending to ORing. And if it is ORing, then we have to make it ending. So here A and B, we can write it as A dash plus B dash. This is equivalent. And here we will write it as B dash plus D. Complement the term literals and ending is changing to ORing. So now our function, minimized function is having A dash plus B dash, C dash plus D dash and B dash plus D dash. So in case of POS, we need 3 AND gate, 3 OR gate and one AND gate. So if we have to draw a logic diagram for this, so we will have OR gate, A dash, or we will have a complement inverter is there. Then we will have B dash. This B dash is common here. Then we have C dash, here D dash, but here we will have D. So here we will have a two level implementation for POS form. We can have an implementation for SOP also. Like here we can draw expression for this expression. We can draw the circuit also. So here we can have an AND gate. And one OR gate. So we are having C dash, B dash, B dash, and D dash, C and D dash. So here we can draw a logic diagram for the minimized expression. So we have covered SOP form, POS form. Now, in the case if we have some input combination for which our function is not neither responding 1 nor responding 0. So, for such cases, we called it as a don't care condition. Like for example, in case of BCD, we have a combination from 0 till 9. But with 4 variables, we have a representation till 11, 10, 11. Like this, we are having 15. So, with 4 variables, we have 16 combination. But valid or important combination is only 10. So, for these remaining 6 combination, we considered our function as a don't care condition, that neither they are having zeros nor they are 1. We consider this don't care as 1 and we will minimize the circuit. And if we have to draw or expression in case of POS form, then we consider this don't care as a 0 and we group with the zeros. Simplification of K-map, and it will optimize our overall circuit. So for this we will have an example that in case of 7-segment decoder, this is our 7-segment decoder where we are representing our numbers in case of on LED, or we can say an LED display or LCD display, where we have to now represent our number from 0 to 9 only. So in case here we have 4 variable input, so there will be a 16 combination. But the valid or important combination are only 9. For remaining from 10 to 15 combination, we are going to make it as a don't care in case of truth table. So here A, B, C, D, E, F, G. So 1, 2, 3, 4, 5, 6, 7. 7 are the outcomes, 7-segment decoder. So these 7 outcomes, we have to make a logical expression for these 7 outcomes. So for this, we will have first go through with a truth table. So in this case, we have this 9 as a valid input combination, for which we make output A, B, C, D, E, F, G as an output high or low. For example, when we have to display a 0, so in case of 0, only G should be off. That G should be not in a glow position or in on position. G should be in off position. Rest of the A, B, C, D, E, F. Rest of the LEDs should be on position. So for 0 case, when we have to display 0, we make A, B, C, D, E, F, G as an F as an on and G as a 0. So to display 1, in case of 1, B and C should be on, others are 0. To represent 2, A, B, G, we can say C and F should be off. So you see that C and F should be an off condition. In case of 3, we will find that it should be F and E should be in off condition. So F and E should be. So in this way, we will make this table. We create this table for 0 to 9 combination. But when we have to simplify, find an expression for A, this A as an output, we have to consider all the 16 outcomes as BCDA as having 16 combination. So when we have to solve a K-map for all these, for this A and B and up to G, we have to consider remaining case also. So for remaining case, that is from 10 to 15, we consider it as a don't care condition. Okay, so here if we solve a K-map for A, here we are having DC and BA. We are naming something like this, DC, BA. So if it is WXYZ, we will use WXYZ as an input variable. If we are using ABCD, we will use ABCD. But here in this example, I am considering it as a DCBA. So I am taking D as an MSB and A as an LSB. So here 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Now, first we will make that after 9, what is the output for 10 to 15. So, it's mentioned that for 10 to 15, we consider it as a don't care. That is cross. So, we will place for 10, so for first we will know the cell numbering. So, we will go with cell numbering 4, 5. So, it's wrong, it's 3 here, it's 2 here. 7, 6, 8, 9, 10, 11, 12, 13, 15 and 14. So, don't care is from 10. Now, we will place 1 because we are making SOP form expression. So, for 0 it is 1, then for 2 it is 1, 3 it is 1, 5, 6, 7 and 8 and 9. So these are the combination where we find it as 1 as a function. So for finding an expression for A, we will now pair it. So we will find, as I told you, we will go with quad. So when we are going to make a grouping of ones, now in this case we consider this don't care as a 1 outcome. And we will make a quad for this. Now in this case it will be an octet. So from octet, like in case of pair, we remove 1 literal. In case of quad, we have 2 literal we removed. In case of octet, we remove 3 literals. 3 literals are changing. So here we find that 3 literals means C is changing, B is changing and A is changing. So only D is with us. And we find that for this octet, only B is not changing. Rest DC is changing, A is also changing. So we have B plus D plus B. Now still we are left with 2 ones We can't leave this as an untouched. We have to make a pair or quad for these one. So if we found that to cover this one, we will have a corner as a quad. Is it okay? Or we can make it folded one, this one, this one, this. It way. Same, both are the same. So here we find that C is not changing, C dash is not changing, and A is not changing. A dash. A is 0, so we represent it as A dash. Now we are left with 1, 1, so we make it as this as a quad. Because to make it octet, we need something here which is not there. It is 0 is there. These two are the 0. So we can't make it a octet for this one. So for here, for this one, we are remaining left with C and A. So for A, we will find this as an expression, minimized expression. But if we don't consider this as a don't care, then what will be the situation? So just we will draw one slightly, we will have one more small K map and just see, so that we will having the expression. So these are the position where we are placing the 1. So in this case, if we go with, we will have only one quad. We don't have any octet, and we will have one pair, this one as a pair, and this is a pair. So we are having 1, 2, 3 pairs, 1 quad. Same, we are having 4 terms, but as you see from this expression, and if we write expression for this, we will see that for A, if we write it here, this pair is there. Here we are having DC, and here we are having, so D dash, C dash, and the value is not changing, is A dash. For this case, it will be D dash, C, and A. Then for this pair, it will be D, C dash, and D dash. And for quad, we can have D dash, and for this quad, we are having D dash and B. So you can find that 1, 2, 3. 3 terms are there, but it is having all the 3 input AND gate, and 1 is 2 input AND gate. But here we will have a 2 input AND gate. So you can see that number of literals are reduced if we go with the don't care condition. And if we here we have not considered a don't care condition. So to minimize, we have to cover all the expression. We have to consider all the input combination. So summary of the CAMAP procedure, that how we are going to start. We have to start with a truth table or Boolean expression if we have any one of them. Then from truth table we have to place ones if we are going to go for SOP form, that is sum of product form. And if we are going to pair of, we have to develop a Boolean expression either ORing. So ORing and then ending is our POS form, and SOP is from ending and then ORing. We have to make a group, we have to minimize it, and then we have to make a minimized expression either in an SOP form or a POS form as per the requirement. So thank you for your time and attention.